Hi, I am Juno and speaking about unsupervised accuracy estimation of deep visual models using domain adaptive adversarial perturbation without source samples. This is joint work with Jeo, Hangyu, and Guanho. The accuracy of a deployed model is often degraded, typically because of discrepancy between the source and target data. Ongoing monitoring of the model's performance is crucial for reliable deployment, but the user lack of target labels poses a challenging problem, unsupervised accuracy estimation or UAE for models. Most of existing methods use labeled source data to estimate target domain accuracy, but accessing labeled source data is often impractical due to data confidentiality or device constraints. Previous approaches generally overlook domain shift issue, which limit their applicability to in-distribution target data. Some employ domain adaptation methods that focus on domain invariant features. However, such approaches lead to suboptimal performance due to label distribution mismatch. To tackle these challenges, we propose a new framework estimating model accuracy on unlabeled target data without needing source samples. Since more accurate approximations of true labels improve estimation, we consider employing source-free unsupervised domain adaptation, or UDA. Source-free UDA enhances prediction on unlabeled target data without source data, so it aligns with our goal of source-free UAE via pseudo-labeling. To this end, we introduce a novel algorithm PAFA that refines existing source-free UDA through self-training. Other source-free UDA methods also fit well empirically in our framework. Though the adapted model has less target risk than the source model, it cannot approximate the true labeling function in general. It often leads to less accurate estimation when naively comparing the two. To address this issue, we introduce adversarial perturbations during inference. Adversarial perturbation promotes the discovery of epsilon neighbors for each target sample that maximally disagrees with its own output. It allows disagreement between the pseudo-labels and the source model outputs to estimate the target risk. For a target sample far away from the decision boundaries, its pseudo-label will mostly agree with its own. But if the sample is close to the decision boundaries, its adversarially estimated pseudo-label may indicate a different class label. This perturbed inference automatically generates pseudo-labels for each data point. These steps from our new source-free UA framework named SFDA-P-ADV. SFDA-P-ADV performs well but faces challenges in severe domain shifts. To alleviate this, we introduce adaptive adversarial perturbations, or AAPs, that adjust epsilon. We employ scaling factors for both individual and collective data. For each target sample, predictive uncertainty refines uncertain pseudo-labels, and we counteract interdomain bias with Jensen-Shannon divergence. Combining these two comes to our adjusted predictive uncertainty. To address discrepancies of data volume density, we apply density ratio. As class count k rises, data distribution becomes sparser, increasing k divergence. We mitigate this by scaling epsilon by log k. These factors contribute to our AAP approach. We investigate the MA trajectory of a smooth epsilon axis across challenging cross-domain scenarios. Applying ADV with a default epsilon of 1 can be suboptimal, as shown by the green dashed line. However, thanks to the adjusted predictive uncertainty, our AAP outperforms the optimal MA of fixed perturbation marked by blue line. Our source-free framework effectively addresses 63 scenarios and outperforms other source access approaches by a large margin. Ablation study confirms uniform epsilon scaling can hurt performance as shown in config 0. But once adjusted uncertainty is applied, including additional factors gradually improves estimation. To summarize, we proposed a novel problem setting and a simple but effective framework SFDAP to solve it by combining source-free UDA and AAPs. This ends my presentation. Thanks for watching.